Hello, everyone. Kommer on, as we love to say in Sweden. I'm originally not from Sweden, but I live here for 4 years. We'll talk today about Firewall and Java and eBPF, something that we discussed over a year back. But before that, quick presentation.
Yeah, I'm Johannes, and I also talked with him a year back. That's why I'm here. So exactly a year back, we talked at JFall, and now we're standing here in front of this real nice conference. And I'm an OpenJK developer at SAP, working on we're like one of the biggest contributors to OpenJK to Java itself. And this is Mohammed.
Yeah, I work for an audio streaming Swedish company, Spotify, and I'm also a Java champion and Google developer expert. And I'm a backend engineer as well, so eBPF part is just for fun. But let's get into the fun. So imagine you have a website, be it your blog, be it as serious as it can be as your company's website. And then you had a very good day and you received a lot of traffic. And then some of the users noticed that and decided to give you some headaches, started to flood you with a lot of traffics. And then you started to bounce your head to the wall trying to figure out how you can fix that. Any thoughts, Johannes?
Yeah, there's a simple way. This is called apply. Thanks for the tech guy for getting me this. This is the Ethernet cable, as you can clearly see, and yeah, we just cut it, and I'm happy that nothing terrible happened. But so essentially, we can just cut the Ethernet cable. Ours or the ones of the attackers, if there aren't that many attackers, and then we're fine. But that's probably not a good idea, isn't it?
Definitely not. Yeah, you don't want to cut all the cables to your servers. So the best second option would be to just build a firewall. And then as crazy as this one sounds, and as ugly as it looks, just like building a firewall in your application layer in your Java app. And this one is just like having a hash table or a map of IP tables, and then add these, and then whenever you receive that request from that IP address, just block it. But I think we can do better. It's like
so we have many problems for this. And the main problem is here we're only, as Mohammed said already, we're only plugging the IP addresses in the application itself, which is not great because you see the whole Linux stack where the packet came through the network interface up through the Linux kernel stack, and then you're like, oh, actually, I don't need this packet anymore. That's not a good idea, isn't it?
No, definitely not, because the latency spikes. I mean, it has to pass through all the network layers up to your application layer and then gets handled there, and then delays the deciding and the action time up until it's reached the application layer, which is not great. The second option is to push it down a layer and push it down to when it belongs to the networks layer. And when it comes to firewalling, the first probably option that comes to mind is IP tables. They are there, they are stable, especially if you're using Linux kernel. You can hijack your code and then just add a little format into it. Trust us, this code works, even as ugly as it looks. With IP tables, you define your rules, and then it would serve as an ugly but working firewall.
But that's not a good idea. And how can we improve it? It's pretty simple. Let's take a look. And you see here that's a thing that's a benchmark that Cloudflare did in 2018, but it's all old today. And essentially, they looked how many packets you can block per second with the different ways. And you see here that IP tables it's pretty fast already. It blocks like on this system 1.6 million packets per second, which is nice.
So we were basically here, somewhere in here, and then we just managed to improve like 2 or 3 times improvements, which is not bad. But we're in the era of 10x developers, right?
So we want to become a 10x firewall, don't we? So
how can we achieve that? And the same company, Cloudflare, managed to push it a little bit forward using XDP. So XDP is Express Data Path, which is a feature within the Linux kernel that helps you to handle network packets at the very bottom level of the networking stack. It gives you tools and APIs and libraries in order to achieve that and handle packets, decide if you want to drop them, modify them, update them, or let them pass. And it's much more faster than AP tables because it gets handled even in the bottom layers of your networking stack.
And so what's fast is let us consider back this. And we know in computer science that allocations are really horrible in our systems because our CPUs got really, really fast. We had like the Moore's law and everything. But if we're honest, our memory didn't get that fast. So allocations are really horrible for our performance, especially when we're dealing with millions of packages every second. And so when a package comes in, we first need to allocate it in a network interface because it's like we have to receive it and even check like Ethernet headers and such. But then there's another allocation, and this happens when it comes from the network interface, like the native stuff, into our Linux system. And then we have another one at the application. So our goal is here to drop the package as early as possible. And as Mohammed already said, we want to drop it in the network interface. We want to drop it after one allocation. And that saves us so much time here.
Exactly. So we are handling the packets as soon as it lands in our network interface, and we will get into that in a minute. But then you can see that compared to IP tables, doing XDP and handling network traffic in XDP is much more optimized and much more faster and resilient. And XDP is...
Oh, and the cool thing is, I might just add, is you can even offload it to your hardware because many modern hardwares implements, new modern hardware implements XDP directly on their systems, directly on the chip, so the packages never reach your CPU, which is pretty cool.
Exactly. So XDP is within the Linux kernel. So the Linux kernel is kind of magical. It has visibility over everything. It handles everything. However, up until recently, if we want to introduce some changes, updates, modifications to the Linux kernel, there are basically two ways to do it. The first way is the hardcore way. So basically, you need to convince the whole Linux community, including the man himself, Linus Torvald, that the change that you want to make is actually valid. It's beneficial for the whole Linux community. So you go through the whole process of writing the proposal, implementing the changes, submitting the changes, and then once it's got merged, do you think it's going to be mainstream yet? Not really, because like the versions that we use, or the kernel version that we use in our OSs is 2 to 5 years delays because the kernel is a critical piece. So all the OS providers wants to make sure that it's stable, and all the APIs that designed above it, it's stable. So you go through all of that, and then you have to wait 2 to 5 years in order to get your hands dirty about it. So that option is, takes a bit of time. And there is the second option, which is
it's called kernel modules. So you can write your own modules that you can just load into the kernel. But there's one slight problem with stability. To quote Greg Hartman, which is like a big guy in the Linux ecosystem, and he wrote somewhere, "You think you want a stable kernel interface, but you really do not, and you don't not even know why you want it." So yes, it's not really stable, and that's a problem. We all know it. When you depend on a software system where the API is specifically not stable, you're all the time maintaining it. And it's good if you're somewhere in like Google or Meter. But if you're like a normal person or even like a software vendor that targets multiple kernel versions, that's not a good idea.
Exactly. And what Greg is trying to say here is like, we have to compromise between stability and speed. And the Linux folks, especially the Linux kernel folks, decided to optimize for speed. Having a stable API means that you need to support APIs for years to come. And if you are maintaining a legacy system, and if you are a Java developer, you know what it takes to support a 20 years old application or 20 years old language. So it takes a lot of time and effort. The Linux kernel folks decided we're going to move fast and break things. And meaning that if you rely on a stable API, that you would need to make those changes sooner or later. So both options are not actually optimal, with either waiting for almost 7 to 10 years to get your work done, or relying on the kernel module, and you're going to be on a one-man land, basically trying to figure this out. Then, is there a third option there available, Johannes?
Anyone?
It's in the title anyway.
We're waiting. We awake, you probably not. It's eBPF. It's the bees come in because we all want to be beekeepers. And eBPF is really cool. It, to quote Brandon Craig, who is most famous on the internet for shouting at hard drives in 2023 or something to simulate, because when you shout at hard drives, they vibrate, so they have different latencies, whatever. He wrote, eBPF is a crazy technology. It's like putting JavaScript into a Linux kernel. Yes, that sounds crazy.
Yeah, I like the analogy of having JavaScript and Java tools, but that's fine. And yeah, that's Brandon Craig with his no shouting and a composed man, and he was one of the early adopters that helped to put this technology forward. But what eBPF is basically a Linux technology, a library, a framework, a tool that enable us to make the Linux kernel programmable, add modules, add plugins to the Linux kernel, make the Linux kernel more modular by adding some plugins and modules to it. And it's event-driven. So if you have to understand one thing about eBPF, it's enabled to add plugins or modules to the Linux kernel in a stable way, and it's also event-driven. So whatever events is happening in the Linux kernel, it can delegate to your eBPF program in order to run, and it runs at execution speed, meaning that the code that we load to the Linux kernel is as it was designed from the ground up, from the very beginning to be executed in the Linux kernel. So it runs super fast compared to running in the application layer. Johannes, do you want to take it over the eBPF runtime?
Thank you. So Mohammed told you the goal is to run as fast as possible. So what do? You take your eBPF program. So essentially, it's when you from the web development sphere, it's like when you attach a hook somewhere, and you have these hooks, and you write some code there. And that's what we're doing here. So we write our eBPF program in a language like C or others you see later, and then compile it down to bytecode, and then the bytecode is loaded into the system. And the cool thing is it then goes through a verifier. Because we're running this code in the kernel, we don't want to trust it to do everything right. Especially, we don't want to have things like null pointer exceptions that we have in Java, where we access a pointer that's potentially null. So what we have for this is the verifying. The verifier is really, really cool. It checks, for example, against null, and it checks that our program terminates. And for all the computer science folks here that think, oh, it checks for termination, that's not possible. It's possible if you constrain your program space, because we essentially say, okay, these programs might only run 4 million instructions all the time. So it's pretty cool. You essentially have a formal verification engine directly built into the kernel.
Exactly. And remember the analogy that Brendan gave? It's like JavaScript for the browser. So JavaScript for the browsers means that it runs within this sandboxed environment and this isolated environment that both ensure security and also stability. And the verifier is where this analogy came from. So the verifier makes sure that the code that we run within the Linux kernel is as safe as it can be. So it have a lot of checks, but also it makes sure that your program is secure. Well, take that with a grain of salt, because if there is one thing that we know in software engineering, is there is nothing as secure as it has. So when it passes the verifier, and if you write any eBPF code, especially production one, the verifier will give you a lot of nightmares. But if you succeeded and managed to pass the verifier, and it gives you the thumbs up, then we take the bytecode that was generated in the first step above and recompile it into native code. And that will ensure that the code that we wrote is actually executed at a native speed. And you can see that we have a modern development framework in the kernel nowadays, which is something we couldn't think of. And also, the change rate is really rapid, so we can have this continuous feedback loop, the continuous deployment come in for eBPF. And that architecture ensures a lot of things. So we're talking about safety and security. Because of the verifier, it ensures that the code that we wrote is actually safe to run.
And the cool thing is also, as Mohammed said, we have continuous delivery. So we talked with people at Meet, and they were like, yeah, before, when we didn't have eBPF, when we wanted to do something like this, doing kernel development, we would have to modify our code, compile it, then ship it to all the kernels on our large test ecosystem, and then wait till the Linux system's rebooted, and then run our benchmarking system again, and it took hours. And nowadays, they're like, oh, I just compile it, I just push it, and 5 minutes later, I'm there. And this ensures that we have fast development cycles, and that means much more innovation in the speed. And it's also efficient, as Mohammed told you before. We have JIT compilers for all the major architectures like x86, PowerPC, or even S390. So if you have your mainframe at home, it will also work fast.
Yeah, and it's standard. So the APIs that comes with eBPF are basically standard. So to include eBPF, the kernel had to go a lot of developments to ensure this plugin-based architecture, but also to ensure that the API that we provide with eBPF, because we're building a platform now, we're building a framework that's enabled to execute all those features, so it's much more stable compared to using the kernel API directly. And then whenever we talk about an application, we need a way to share the data, right?
So typically when you're doing like normal software development, you have two ways. You can use sockets. It's like essentially like we do in the web. We send a message, we receive it, and that's fine. Or we could use shared memory. We both access the same memory, but that's not that good of an idea in kernel development, isn't it?
Oh, no, definitely not. So if either the socket option or the shared memory option that we use in modern applications today, either distributed or in-process application, especially if you're sharing it within the kernel, there is a lot of options that come with it, especially from a security point of view.
So the main issue here is that when we're working with shared memory, we have synchronization, and when we're working with sockets, it's slow. So we want to have something better.
Yeah, and the kernel folks came up with eBPF maps. The name in here is very weird. Even the name eBPF I found a lot of issues with. But maps are basically boils down to be data structures. So those are familiar data structures, maps, arrays, hash tables, kind of lists. So all of the traditional data structure that we use in our daily job as developers are actually available and managed by the kernel. Because when you're dealing with the kernel, you want the kernel to have full control and full visibility over what's passing through the user land and the kernel land. So those are basically data structures that are provided by the Linux kernel. And the good thing is you can write them both ways. So you can use eBPF maps to save data that your program will use. You can use eBPF maps to share the data with the user land program that can read those data for performance analysis, for logs, for everything. This is one of the use cases that eBPF is used for. And then you have an application user-led program that reads the data. Or you can write configuration options from the user-land program to your kernel program using maps. So it's both ways. It's bidirectional. And you can basically use it for whatever scenario you might think of.
And there are many, many maps. As Mohammed told you before, there are hash maps, even with last recently used semantics. It's really nice for caching. There are arrays and ring buffers. And the cool thing is, if you ever develop some C code and you wonder, like, how do I get a hash map without including like the boost headers? That's your way here. And that's really cool because it makes eBPF development so much easier because these are fast, tested, and directly built into the kernel data structures. And there are so many, we couldn't even list them all here.
And exactly.
Yeah.
And then hooks. So I mentioned in the very beginning that eBPF is event-driven. So in the event-driven world in eBPF, they call it basically hooks. So hooks are basically attachment points or events that you are interested to handle. And looking at the top, everything that is started from the system call, whatever system call you want to handle, call to your to another application, to another process, or whatever, it basically can be handled and attachment points to your system, and we will have a demo for it soon. If you want to handle packets, you can do it as multiple levels and multiple layers within the networking stack, sockets, TCP. If you want to listen to the allocating memory, opening files, whatever, this also can be done. And then, as Johannes mentioned earlier, with eBPF, there is eBPF offloading, and one of the great examples is the XTP offloading, which means that if you have a specific hardware type and that supports eBPF offloading, you can offload and the execution of the program off CPU to that hardware So for XDP offloading, for example, you offload the execution of your eBPF program to the network card. So the network handling will happen on the network card before even it reaches your CPU. So all that work that happens within eBPF, within the kernel, is basically handled off CPU, which adds great speed and great performance for your application.
And you can attach it almost anywhere. You can use it for tracing, profiling, for observability, for monitoring. So it's a tool it's a technology that come into our world like a few years ago, but now it dominates many parts of the industry, which is pretty nice. You could even use it for security control. And we've all seen CrowdStrike. I don't know, were you affected by CrowdStrike?
Yeah, I was in a conference in Berlin, and then my flight was cancelled because of the CrowdStrike. But yeah,
But when we have eBPF now, this shouldn't happen because, like, hey, CrowdStrike was allegedly caused by an array where they read out of bounds. With eBPF, the verifier is like, wait, you're doing this? But eBPF has its own problem, doesn't it?
Exactly. So as any software in the world, basically, it comes with its bugs, it comes with its flaws, basically. And it's a technology that keeps evolving. They are doing as much as they could to ensure the security, stability, and everything, but it's still a work in progress, but evolvable work, basically. So it's as stable as it can be of the things that we know, but there are always room for improvement. And it's something that you need to consider as well.
So don't run any eBPF programs that you don't trust. Don't run eBPF programs from me on your production servers because I can't be trusted in this regard. Don't only run it from people that really know what they're doing because it can have access to everything, essentially. Yes, it's kind of secure, but it can have access to all parts of your memory. You're running this with kernel privileges. So just be aware of this.
Exactly. And for the ecosystem, we can start from the use cases, basically. We mentioned security. That was the original use case that eBPF or BPF basically was born to. And then we figured out that the architecture is so flexible that we can do other things like security and observability and tracing. And there are multiple tools there. So there are multiple tools that you can use. Pixie for observability, for example. Katran is an open source tool networking from Meta. So everything that is coming or going from Meta is going through Katran. Cilium is the cloud native networking tool. So there are a lot of tools in there. And then if you want to build things your own, there's a lot of SDKs. For Go, C, and Rust, there are multiple languages that are supported there. And then we talked about the runtime. However, one question: there's a language that is still missing in that in the SDKs.
Anyone?
What language is this?
Anyone? Python has already one. It's the BCC.
Yeah.
C#, nah, that's Windows. Java, yes, that took a while. I thought we made it obvious. So to quote Brendan Craig again, eBPF is a great technology. It's like putting Java into the Linux kernel. And yes, that sounds crazy. I once was a couple of weeks ago at a Linux kernel conference, and they were like, oh, I thought it was a joke when someone else told me that you're doing eBPF and Java. But anyway, I want to use a programming language which doesn't only run on userland to grow the famous trailer for a nice conference in Oslo. Anyway, that's Hello eBPF, and that's what I worked on in the last couple of months. And it's the first SDK that allows you to write eBPF in Java.
Exactly. And it's still a work in progress, and we were running a bit fast in this first pass of presentation to save a lot of time to basically work on the demo. It's still a work in progress. Johannes made a very good progress compared to it, but yeah, if you have any feedback, features, please scan the QR code and come up with suggestions, improvements, bugs. It's always helpful.
And so it's based on so I also wrote a blog series on, so you can find all the resources on the last slide, so you don't have to copy anything. There's all the demos is online, so you can check it out yourself and ruin your system. The thing is, that's why it's only a second time where I'm doing this actually on a Linux computer directly, so everything is running here, so let's hope it works.
Yeah, time for the live coding session. And the reason, while you're setting up your environment, the reason why we're switching to Linux instead of Mac, so we were in a conference last month, and then Mac didn't work because we needed the Linux kernel, so we were using a VM, and that's, was not pleasant, to say the least.
The problem was it crashed our system because I only had 16 gigs of RAM, and when you're running a VM in it and some IntelliJs, that's not good. So this here is a nice machine, and now I'm doing live coding as I would want to call it having fun with eBPF and the verifier. As Mohammed already told you, the verifier can be kind of a pain in the ass. And so,
Hello?
hello, okay. Yeah. So now we're starting with the demo. So
can you make the code a little bit bigger?
You can see it? Okay, thank you. It's always interesting.
Yep.
Can you see it now, or should I make it even bigger? Okay. So essentially, we need pseudo privileges. That helps. Let's see when I. The problem is we need to have Java in the pseudo environment. So.
Yeah. Basically, we are dealing with the Linux kernel, and everything that needs to run in the Linux kernel needs root privileges. So that's why some things to keep in mind from a security point of view. You don't want to give everyone that access, and you don't want to run anything that you don't trust in that environment.
So we pre-compiled before, but essentially we want to show you a firewall so that you don't think that, yay, they talk about the firewall in Java, they just mocking us. So we're like, ta-da, we even use Spring. That's a web front end and a Spring application written by our trusty friend ChatGPT, because I'm not a web developer. Are you a web developer?
Sometimes.
Oh, yeah. It's probably not a good... No, we're just joking. We work on different things, so that's what we're doing here. And so we open this here. It's essentially a web front end for our eBPF, and the cool thing is that passes the data directly into the kernel without any checks. And yes, this is a good idea. So essentially, the idea is here we create a firewall rule. The firewall is pretty simple. We just block all HTTP access. That's the reason why I downloaded the presentation before from Google. Otherwise, we don't have a presentation here anymore. So we sent a JSON, and what you can see here, we try to access it, and we're already accessing it, probably because some of the presentation still talks to Google. Anyway, you see it here, we block packages all the time, and that's not great, but we can reset the rule, and then everything works. And that's a functional firewall that blocks packages written in Java, which is pretty neat, I think.
Yeah, indeed. And you can see that the application is written in Java. Written in Java in an application. We have the userland program, which is the Spring application that's basically write configuration. The firewall rules, you can think of them as IP table firewall, but those are eBPF. So we take those rules that's written in our userland application Spring Boot, we translate them to eBPF, and then we load them into the Linux kernel using eBPF maps. And then the one that does basically the blocking is the eBPF program in the Linux kernel. Can you walk us through the code, Johannes?
Yeah, but I think the code is a little bit too complex. If you might see, it has like lots of lines and everything. So let us start maybe with a small example.
Yeah.
We probably still have like 15 minutes time, so
yeah.
That's fine. I'm fast at coding. I never learned 10 fingers. Anyway, what we want to do in our simple example, what we in the beginning do, we write our Java application, and so we have to tell our Java application, hey, we want to have this something eBPF related, so we extend the eBPF program class. And because we want to because we're doing something networking related, what we do is we also implement the interface XDP hook. So that's what gives us this hook that we can implement. So what we can do is we override, let's see what we can override. The method, the couple is really wrong here. We can override, let's see, override implement method. So there's the network hook method. Oh, here, there's when we handle packet. And so that's essentially, now we can, when we, for example, want to print a packet, we get from the context, we get all the packet information. We have to parse it ourselves, so I needed to learn how to do packet parsing again. I only did it in uni, but we want to do a simple example, and for this simple example, what we want to do, we want to have a global variable count, so we drop every third packet. So that's pretty simple. We have an unsigned integer, and we call it count. So it's initialized by 0. And so yeah, now we like software architecture, we learned it's good, so we create methods. So what we do when we create a method that runs in the kernel, we call it a BPF function. And so what we want to do is public boolean drop packet. And what this essentially does, it can either return true, but what we really want to do is like, for every third packet, so we get the value, we take it modulo 3, and we say, oh, every time modulo 3 is 1, we do it. And so what we do here is count set, count.get, so we essentially just increment it. And then we just say, when we drop the packet, then we drop it, else we pass it. It's pretty simple, but now we have to have some way to attach it, don't we?
Yeah, exactly.
Because this doesn't do anything. Any idea? We need a public say void main method. It's still Java after all. So what we do, here, we tell XCP attach, so it attaches this to the incoming network interface, and that's all. We print something. We can even be like, oh yeah, we just, I don't know, we can print something.
So those 3 lines are basically what we explained within the architecture. So we wrote our eBPF program, and then since it's event-driven, we need to load it to a specific hook, and then we attach it to XDP, basically. So we're interested in XDP events, and then the last sentence is basically to print some events, some trace, print some logs.
And the cool thing here is this code here runs in the kernel. This code here is used by both. This code here runs in our userland, and it's pretty cool because we essentially write it in the same application. We don't have to repeat ourselves because we could even like use this drop packet method both in the Linux kernel and both in our Java application. Now we just compile it while Mohammed was on it, and it lives in demo.sample. Hopefully it runs. That's always a good sign. Oh, interesting. I think the main problem is I'm running a secret demo alongside, so I just recompile it, and because there's only one like trace, there's only one output stream per system. So anyway, so you see you get lots of errors sometimes when you do development. It's kernel development.
Johannes didn't mention it, but it integrates with Maven and stuff. So there's a plugin that compiles, when you compile your code running Maven, it basically generates the binaries that handles everything and exports everything to be executed within the Linux kernel. It takes some time, but
it does a lot of things.
Sometimes it's
Now, the problem is you can't see anything, but I hope you can trust me, it drops every third packet. So we can probably see this by pinging google.com. And this should have, and ping should have problems because when we drop every third packet, ping is like, what are you doing? And you see here, normally we would expect google.com to be accessible. No, it isn't because we drop every third package. Anyway, but how does this work? It's not that hard. We skip over some things. It works based on Project Panama, so you have Java's new FFI interface, which lightly allows me to write code that directly accesses the underlying C library that deals with the system call stuff for me, which is pretty nice. But yeah, how does it work? Can you explain how does it work from Java code to C code?
Yeah, so from the Java code, we have annotation processors. So Johannes went through and went crazy with annotation. You see that eBPF and all of that. So all those are annotations. And we have plugins behind the scenes that basically go through all that annotations and basically process them and have them as aligned and defined. And then we take that, and then during the compile time, that's where the magic happens. We have basically mappers over everything. That's basically analyze the code, analyze the execution path, and then generate the equivalent C code that gets executed within the Linux kernel.
And that's a really important thing. So I translate so help eBPF translate the C part of your code, the code that you want to run in the kernel. It translates it down to C code, and Halo eBPF deals with everything like mapping structs, so you can map structs to C structs and classes to C structs, and also parse back the thing from memory. And for the compile nodes here, you can look at the slides later, but you essentially the Clang then compiles it down to eBPF bytecode. It's pretty simple to understand.
Yeah, it looks like assembly at some point. But yeah, so the goal here and why we are doing this presentation and Johannes investing heavily in this library is basically to make Java as a kind of good citizen, if not the first-class citizen when it comes to eBPF development. We're still a long way to go, but yeah, we just started our journey.
And it's a way towards marker call. So the eBPF in a whole, because we're essentially taking code that was previously custom written into the Linux kernel, we're pulling it out, pulling much more functionality out, so that the user can exchange it, and it makes the Linux kernel so much more flexible.
Exactly, and eBPF would hopefully making kernel fixes a lot more fast and a lot more painful, less more painful, sorry, not a lot more painful. So for CrowdStrike, for example, if it was, let's imagine a zero-day vulnerability like CrowdStrike, having an eBPF fix that can be basically loaded to every Linux kernel, waiting for that Linux patch and update, which would take probably some time. Having the Linux eBPF program that's got deployed over to patch all the affected machines and servers would basically be an option. So having an eBPF program that fixes, hot patch the issue, and then until we have a proper fix within the Linux kernel, that could be one way that we can make our system more secure.
And the cool thing is here, there's also, it's new, it will come into the next Linux kernel. It's the scheduler, it's the Linux scheduler extensions with the Sexobot. That's the official logo here. Essentially, it's for the Linux people here. It's really nice. And the cool thing is, you might have noticed, some of you, that there was a terminal running here. It's because it showed something else, but essentially what was running alongside it, and probably stopped some time, was that most of the presentation ran with a Linux scheduler that was written in Java. So the Linux scheduler that ran most parts of this application, of this talk, was this here. You just implement the scheduler interface, and you can write your own Linux scheduler because you can. Don't ask me why, but it's cool for educational purposes. That's what I told my boss. So yeah, thank you for being here. It was great to talk in front of this large crowd. It's always nice. I want to say thank you to of course, Mohammed, who gave the talk with me. I want to thanks to Dylan Ramming, who helped with the eBPF part, to my team at Submachine. We're like one of the biggest contributors to the OpenJK, bringing you such gems like the new null pointer exceptions that you found that gives you information on what happened. You'll find all the resources and many more things on the QR code. And when you want to read more, I write blog posts regularly on these topics at Mostly Nerdless, and you find me on social media somewhere. And probably I find you also on social media.
Sometimes, yeah. So yeah, thank you everyone. Thanks for joining. We still have 2 minutes for questions. Yes.
Essentially, the question is what kind of protections are there against accessing? Pretty simple. You need root privileges. You need the eBPF capability to access these maps. So essentially, when you have root, everything is off anyway. So that's the main protection.
How long does the module live? I see that they attach things.
Yes, the module lives as long as the Java application lives. When it closes, it's implemented. When it closes, it unloads it. It's via the shutdown hooks. It works pretty efficiently. If I'm honest, I think, no, it's essentially, for the Java nerds out there, it's a try with resources, so it's closed after this finishes. And also, if it hasn't closed already, on the shutdown hooks when something terrible happens.
Yeah, but in general, eBPF programs can live forever until you detach them basically.
A last question now, anyone?
So when you will have events, so you would need to imagine that you have a package network vulnerability, like sorry, you have a faulty network packet that is coming that breaks your system down. So you would attach it, for example, to one of the network hooks, probably XDP, and then read the headers, and then network packet that is have a specific header, just basically drop it. So we would load that, the small eBPF program that check the header and then make it drop as Johannes Mohammed, like XDP drop. So we can load it, read the header, and then drop it. So basically, if you have multiple events, multiple hooks destined to the same events, basically it will dispatch to them. And then the decision would be if an OR basically.
So yeah, kind of the main issue is when the main question was when you probably have multiple hooks there, you most probably get some errors. So and you have with networking you have orders, so you can create queue disks, and thereby you have some ordering. So if you want to know more, there are enough eBPF people that know much more than we both. Just ask the Sicilian people; they had lots of trouble with this.
Yeah.
Anyway, I think that's all. We're 1 minute over. Thanks for all being here. It was a really great conference. Thanks for Øredev for having both of us here.
Yeah.
And so have a nice last day of the conference and have a nice weekend.
Tak.